Ever looked up at the night sky and wondered about its deepest, darkest secrets? Today we're going on an epic adventure, a journey to the most mysterious objects in the universe, black holes. But we're not just stargazing. We're going to dive right into the heart of one, using the language of the cosmos itself, mathematics. Don't worry, you don't need to be a genius to follow along. We're going to break down the mind-bending equations that describe these cosmic monsters into something we can all understand. So, buckle up, because we're about to journey to the core. First things first, what even is a black hole? Imagine a star, much more massive than our sun. For its entire life, it's in a constant battle with itself. The nuclear fusion in its core pushes outwards, while its immense gravity pulls inwards. But when that massive star runs out of fuel, the outward push stops, gravity wins. And it wins in the most spectacular way possible. The star collapses under its own weight, squeezing an incredible amount of mass into an infinitesimally small point. This point is called a singularity. The gravity here is so strong that nothing, not even light, can escape. That's a black hole. Now, how do we even begin to describe this with math? We need to call in the big guns, Albert Einstein and his theory of general relativity. In 1915, Einstein completely changed how we see gravity. He said gravity isn't a force pulling things together like Newton thought. Instead, it's a curvature, a warping of spacetime itself. Imagine a bowling ball on a trampoline. It creates a dip, a curve in the fabric. Now, if you roll a marble nearby, it doesn't get pulled by the bowling ball. It simply follows the curve created by it. That's gravity. Massive objects like stars and planets bend spacetime, and other objects just follow those curves. A few months after Einstein published his equations, a brilliant physicist named Karl Schwarzschild did something incredible. While serving on the front lines of World War I, he found the first exact solution to Einstein's equations. And what did that solution describe? A non-rotating, uncharged black hole. This is our blueprint, the classic model. Schwarzschild's solution gave us a crucial concept, the event horizon. Think of it as the point of no return. It's not a physical surface you can touch. It's an invisible boundary in spacetime. Once you cross it, the escape velocity, the speed you need to escape the gravity, becomes greater than the speed of light. And since nothing can travel faster than light, you're trapped. Forever. The math for this is surprisingly elegant. Schwarzschild's solution gives us a specific radius for any given mass, now called the Schwarzschild Radius. The formula is R equals 2gm over c squared. Let's break that down. R is the radius of the event horizon. G is the gravitational constant, just a number that tells us how strong gravity is. M is the mass of the black hole. And c is the speed of light. So, the more mass you cram into a black hole, the bigger its event horizon gets. For an object with the mass of our sun, the Schwarzschild radius would only be about 3 kilometers. Imagine our entire sun squeezed into a ball just a few miles wide. Earth's would be the size of a peanut. So, what happens if we actually fall in? Let's imagine we're in a spaceship, observing a brave astronaut, let's call her Alice, who is falling toward the event horizon. From our safe distance, we'd see something really strange. As Alice gets closer, time for her would appear to slow down. Her movements, her clock, everything would seem to be in slow motion. As she reaches the event horizon, from our perspective, she would appear to freeze in time, her image getting dimmer and redder until she fades away completely. We would never actually see her cross. This is called gravitational time dilation. The intense gravity is literally stretching time itself. But what about Alice? What's her experience? For her, nothing special happens as she crosses the event horizon. There are no alarms, no flashing lights. She just floats right through it. But once she's inside, her fate is sealed. Inside the event horizon, space-time is so warped that all possible paths, every single direction, lead to one place, the singularity at the center. It's not like trying to swim against a current. It's like the future itself has been replaced by a single point. The direction forward in time, becomes the direction toward the singularity. There is no escape because escaping would mean traveling backward in time, which is impossible. Now, what is this singularity? According to the equations of general relativity, it's a point of infinite density and zero volume. All the mass of the black hole is crushed into this single, dimensionless point. Here, the curvature of spacetime becomes infinite, and our laws of physics, including Einstein's own equations, completely break down. They give us nonsensical answers, like dividing by zero. This is a huge signpost for physicists, telling us that our current theories are incomplete. We need a new theory, a theory of quantum gravity, to understand what truly happens at the heart of a black hole. This is one of the biggest unsolved mysteries in science today. But wait, not all black holes are simple non-rotating spheres. In reality, most things in the universe spin. Stars spin, galaxies spin, and so when they collapse, the resulting black holes also spin. In 1963, a mathematician named Roy Kerr found the solution to Einstein's equations for a rotating black hole. And this is where things get even weirder. A Kerr black hole is different. Its singularity isn't a point, it's a ring, a ringularity. The rotation also drags spacetime around with it, in a phenomenon called frame dragging. This creates a region outside the event horizon called the ergosphere. Inside the ergosphere, it's impossible to stand still. Spacetime itself is spinning faster than the speed of light, so you're forced to move with it, even if you fire your rockets in the opposite direction. What's wild is that it's theoretically possible to enter the ergosphere, steal some of the black hole's rotational energy, and then escape, coming out with more energy than you went in with. This is called the Penrose process. It's like a cosmic energy heist. And the journey into a Kerr black hole is even more bizarre. Because the singularity is a ring, the Kerr solution suggests that it might be possible to avoid hitting it. The equations show a path where you could, in theory, pass through the center of the ring. And where would you end up? The math hints at something called a wormhole, a theoretical tunnel through spacetime that could connect you to another part of our universe, or even another universe entirely. Now, before you pack your bags, this is highly speculative. Most physicists believe that such a wormhole would be incredibly unstable and would collapse the instant anything tried to pass through it. But it's a mind-blowing possibility that comes directly from the mathematics. So, from the simple elegance of the Schwarzschild Radius to the swirling madness of a Kerr black hole, ringularity and potential wormholes, the equations of general relativity paint a truly incredible picture. They take us on a journey from the edge of what we know to the very breakdown of physics itself. These cosmic giants aren't just destructive voids. They are laboratories for extreme physics, pushing the boundaries of our understanding and pointing the way toward new discoveries. They show us that the universe is far stranger, more complex, and more wonderful than we could ever imagine. The journey to the core of a black hole is really a journey to the edge of human knowledge. Thank you so much for joining me on this cosmic deep dive today. I hope it sparked your curiosity about the incredible universe we live in. If you enjoyed this video and want to explore more of science's biggest questions, please hit that like button, and don't forget to subscribe and turn on notifications so you won't miss our next adventure. Got any questions or ideas for future topics? Drop them in the comments below. Stay curious, and I'll see you in the next one.